These are the equilibrium expression notes, or the KEQ notes. You're going to start by talking about equilibrium expression concepts first, and then the mathematical notes will be in a different video. So as we're looking at reversible reactions, we are going to write equilibrium expressions, or KEQ. Equilibrium is for EQ expressions. And what these are ratios that show the relationship between the products and reactants when you are at chemical equilibrium. And this relationship is based on concentration. And so to denote or to easily show we are representing a concentration, we use square brackets. And that just kind of makes it so we don't have to write concentration of. We can just put a chemical in square brackets to show that's what we are looking at. And a reminder that the unit of concentration is molarity, which is moles divided by liters for a solution. And because we're looking at equilibrium, how can concentrations change? The only things that we are going to include in these expressions are gases and aqueous solutions. With that, it is easy to change molarity of gases and aqueous solutions. Those can change. What's not included are things that can't change. Solids are always going to have a concentration of they're pure. So it's not going to really have a concentration for when we're looking at these kind of pure substances. So we just say we just have this solid, we have this liquid. So because those are pure, their concentrations can't change. Gas and aqueous, though, these can have we can vary their concentrations with that. And so that's why we can look at those two when we are looking at our equilibrium expressions. As we are looking at our balanced equations, those are going to become coefficients, or coefficients from our balanced equation are going to become exponents in our expression. And so here's an example of an equilibrium constant expression. KEQ is the concentration of our products over concentration of our reactants. And we've got a reversible reaction. We still always are going to use what is on the left side as our reactants and the right side as our products. And we are going to write that expression looking at the concentrations of anything that can change. So let's go ahead and look at this. We have some reversible reactions, and let's write those equilibrium expressions. Nitrogen gas reacts with hydrogen gas to form gaseous nitrogen trihydride. I have my equation here. I have my states of matter. This is balanced. So in order to write that KEQ expression, and as a reminder, that KEQ expression is going to be the concentration of our products over the concentration of our reactants. And so we've got KEQ, EQ again for our equilibrium expression, concentration of our products. Well, we have our products on the right, our reactants on the left, and we need to look at, can we include these? Gas, 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 all of these are going to be included because all of those can change concentrations. So we've got the concentration of, well, my product, I only have NH3, and so I'm going to do concentration of NH3, but because I have two of those, that coefficient is going to become an exponent. That's the only reactant or product that I have, so it's the only thing that's going to be in that numerator. As we look now at our reactants, we are going to do the same thing. I have nitrogen. I only have one of those, so I'm just going to do concentration of nitrogen, and this is times the concentration of my hydrogen, but I do have 3 hydrogens, so that coefficient is going to become an exponent. And this is my KEQ expression for that first equation. Looking at the next one, we've got a reversible reaction written out for us. Solid lithium reacts with liquid water to produce hydrogen gas and aqueous lithium hydroxide. In this KEQ expression, we only can have things that can change concentration. So looking at this, a solid can't change concentration. A liquid can't change concentration, only gases and aqueous. And so gas and aqueous, Those two are going to go in our expression, but our lithium and our water cannot. So as we're going through and writing our expression, we are going to include products, concentration of products over reactants. My products are hydrogen, so I'm going to include hydrogen, and my lithium hydroxide solution. That LiOH has a 2 in front, so that's going to become a exponent. And then what's going to go on the bottom? Well, really, these have concentrations of 1, and so those aren't going to vary, so that's why we put a 1 in the denominator. Go ahead and try number 3 on your own if you want. Gaseous carbon trihydride reacts with oxygen gas to produce carbon dioxide and water vapor. Looking at this again, I want to look at what can I include in my expression. All of these are gases, so all of them can have changing concentrations. And so we're going to have Keq, and that's going to be products over reactants. I've got CO2, but I have 3 moles of that, so CO2 cubed. I have H2O, but I have 4 moles of that, so to the 4th, all over C3H8. I only have 1 mole of that, but it still needs its own brackets, times O2 concentration, and that is to the 5th. So again, any of our coefficients become subscripts, become exponents when we are looking at going from our reversible reaction to writing our Keq expression. And one thing, we haven't done calculations yet, but Keq is not going to have any units on it. It is a expression that is going to tell us about how our equation is, or what our reaction is going to look like when it reaches that equilibrium. So what does the magnitude of that Keq value tell us? We're going to have 3 options. We're going to either have a K value equal to 1, a K value greater than 1, or a K value that's less than 1. These are always going to be positive. And so if K is equal to 1, that means that the product and reactant amounts or concentrations are the same, so neither side of the reaction is favored. So this is going to tell us how are we seeing these reactions or these chemicals show up when we are at equilibrium. If K is greater than 1, that means more products are there at equilibrium, so it's product favored. If K is less than 1, that means we have more reactants at equilibrium, and so it is reactant favored. And this should make sense if we look back at this equation that we have. We've got that as we look at how do we write these Keq expressions. Well, if we have our products favored, that means the number on the top is bigger. Well, that's going to be a greater than 1. If our number on the bottom is bigger than this one, our number is going to be less than 1. And so that's how we're going to get our reactants being favored. How can we model this? Well, we can model this by kind of drawing out and just kind of using this space. And we're going to just show how they are sharing the space. This doesn't have to be a perfect ratio. And so when we're modeling it, let's just show how they are sharing the space, the products and reactants. All right, and so let's look at this one. We have Keq of 0.1. Well, that is a Keq of less than 1, which means that this is going to be reactant favored. So we're going to have more reactants. We can show this and so here we have our reactants and our products. We don't necessarily know the concentrations of these. You could, if you want, go through and say, all right, we've got nitrogen, and then we have those hydrogens. We have 3 of those. And if this is going to be reactant favored, we're going to show those occupying more space in this beaker, which means that we would then have our NH3 taking up less space. And so we've got more reactants than products, as we're looking at sharing the space. So I'm just showing reactants occupying more space. If you want, you can write these out by those chemicals, or we could also just show that with a beaker. If I just copy one of these, we could also just show that with, let's say, reactants taking up a lot of space, products taking up less space. So you could also model it like that as well. Let's go on to the next one. Keq equals 1.0. Well, that 1.0 now means that whatever is in the numerator and denominator of our Keq expression, products to reactants, that's a ratio of 1. So the amounts are the same. Neither side is favored. We're going to see both products and reactants represented the same. And if we look at that, I can kind of model that two ways. I could show that as, and again, I can write out, and I'm going to split this in two, and I'm going to say splitting this in half, we would have our reactants taking up half the space, and I am showing that 1:3 ratio if I need this, and then I have two NH3s, and those NH3s are taking up the other half of the space, so we would have those same concentrations. We could also show this with a equal split here of our products to reactants with that. I don't know if that looks super equal. Let's make it a little better. All right, last one. If we have a Keq of 10, well, Keq of 10, that is a greater than 1, which means we have more products. So this number is bigger than this one. So our products are favored, and so we've got that Keq greater than 1, products favored. And so now I'm going to show my NH3 taking up a lot more space, and I'm going to have less of those nitrogen and hydrogens, even though that ratio stays the same. And again, we could show that with less space for our products, more space for our reactants. Modeling this way allows us to kind of see which of those actually are, and kind of gives us that better visual of what are those products versus what are those reactants as we are looking at that. So these are the basics of just the concepts of equilibrium and how we use that Keq value. In the next set of notes, we are going to look at doing calculations with those Keq values and what those can help us find.